Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to introduce Mikhail Rouvier today. Mikhail comes to us from Marseille in France. He's had a long trip. Prior to his postdoc position at the University of Marseille, he obtained a PhD at the University of Avignon. While he was there, he developed a super elegant way of doing diarization that basically reduces the problem to 0-1 integer linear programming. And today he's going to tell us about that and then some extensions that use embeddings to do diarization.
Thank you. Thank you, Geoffrey. I want to thanks for the invitation. I'm very happy to be here. So today I will speak about speaker diarization, and I will speak about optimal clustering using integer linear programming, and after I will speak about speaker embeddings. So the outline of my presentation. So first I will speak about me, so about my project and my background, and after I will speak about speaker diarization. I will just briefly describe what is speaker diarization, and I just describe speaker diarization apply on broadcast news, not in meetings. There is some difference. So during all my conversation, I just present speaker diarization, I apply on broadcast news. And after I will speak about speaker clustering. I will present the method ELP clustering. So the ELP clustering was very appreciated by the community. In fact, when I sent the paper in the conference, Najim Deak and Patrick Cleany sent me an email. So Najim proposed to come to the MIT in order to present this method, and Patrick wants to reproduce all my results. And after, during the conference, many people asked me to send the code, to release the code about ELP clustering. And after, I will speak about speaker modeling and how to extract relevant information on speech segment using deep neural network. And I will present you this method that I call speaker embeddings. So what about me? So my name is Michael. I'm 33 years old. I come from France. France is near England, Germany, Spain. So I'm very apologetic because my English is not perfect. It's not perfect, it's very bad. So if you don't understand, please stop me and ask me to repeat. Or you can stop me during the conversation to ask me every question. So I obtained my PhD in 2011 in Avignon, and I work on video summarization, automatic video summarization. Then I moved 2 years old in computer aided science of Le Mans. I work on automatic speech recognition and speaker diarization, and after I moved at Marseille in computer science of Marseille, and I work on extract relevant information using deep neural network. Oh, sorry, I just forgot to say this is Avignon, Le Mans is located here, and Marseille is located here. So I just present two projects, two interesting projects that can be interested in Microsoft. So the first one is Roper project. So this project consists in identify the person in TV show. So we can identify the person on the video, but also on the audio. And here, by example, if you want to identify this guy is Jean-Marc Ayrault, we can use a face ID or speaker ID, but you can also use all the other information. By example, this information, the name of the guy is right on his ear, or the name of the guy was spoken the last segment, and you can propagate all the information in the video. So during this project, I work on automatic speech recognition, on speaker diarization, and on speaker identification. but I also work in the propagation of all the information around all the modalities. So the second project is the BOLD project. So the goal of this project is a machine-mediated bilingual conversation. So the main idea was to go beyond the simple pipeline, automatic speech recognition, and machine translation. So one of the goals of this project was to detect the error and so the machine must detect the error and to ask to the user to repeat the sentence. By example, if the user say, "I like your beret," and the system doesn't know the word beret, the system say, "You like what?" The user say, "Your hat." So the system merge the first sentence and the second sentence and try to create the sentence, "I like your hat," and translate, "J'aime votre chapeau." So I worked in a lot of fields, but one of my goals was to extract relevant information from documents. So I work in speech, image, natural language processing, machine learning, and information retrieval. The number that you see here is the number of publications in each of fields. And now I try to work in extracting features using neural network. So so what about speaker diarization? So the goal of speaker diarization is to answer to the question who speak and when. So given audio stream and broadcast news, we can solve this problem in 3 steps. The first step is to detect the speech and non-speech segment. And after we take only the speech segment and we do a segmentation in order that each segment contains the voice of only one speaker. And after that, we done clustering. So we try to say that, for example, this speaker and this speaker are the same speaker. So in my presentation, I just focus in the last steps, speaker clustering, and I propose a new method about optimal clustering. So in speaker clustering, there is 2 kinds of approach. So the first approach is the hierarchical clustering, like bottom-up or top-down, that consists at each iteration to increase or decrease the number of clusters. The second kind of method is partitioning clustering, like k-means or mean shift, and consists to refine the partitioning during each iteration. So concerning the bottom-up algorithm, so the bottom-up algorithm is an iterative algorithm that merges the 2 most similar clusters, but there is some limits about this kind of approach. First, it's a greedy algorithm. By greedy, I want to say that at each iteration, they take the best solution, but we are not sure that the best solution is the best solution at the end of the process. And the second problem is that the bottom-up algorithm never considers the decision. I just want to say that if an error is done, this error is propagated along all the process. So the second algorithm is the partitioning clustering, by example, the k-means algorithm. And the k-means algorithm try to minimize an objective function, by example, the distance intra-class. But there is some problem. The first is that the number of clusters is fixed. And in the case of speaker diarization, it's a problem because in speaker diarization, we don't know the number of speakers and we don't know who speak in the audio stream. So there is a problem here, and the second problem is that about the initialization of the cluster. So if we badly initialize the cluster at the beginning, we can fall in a local optimal solution and not to the global optimal solution. So I like the idea about partitioning clustering because there is an objective function. but we must to tackle the two problems. That the first one is the problem of the number of clusters, and to tackle the second problem is the problem of initialization of the cluster center. So in order to tackle the second problem, I propose to use the integral linear programming. So integral linear programming is mathematical models that can, so given an objective function and some constraints, we can obtain the optimal solution of this problem. So how does that work? So we give an objective function. So if we want to minimize or maximize, the objective function is a linear function with some integer variable, some binary variable, and we give some constraints like a linear function. After that, we can use like an algorithm, branch and bound algorithm. This algorithm will remove all the fruitless candidates during the research of the best solution. So one of the goals of the problem is to express the clustering problem as an ELP problem. So in order to do that, we assume that the center of a cluster is necessarily a point of a problem. So how to express in binary variable this problem? So I want to say that this segment is in the same cluster and this segment are in the same cluster. So first we enumerate all the points, 1, 2, 3, 4, 5 to 10. And after we say that the segment 4 is the center of the blue cluster, and that the segment 9 is the center of the red cluster. And we assume that all the points that beyond this threshold belong to this cluster. So in order to explain this in a binary variable, we create a matrix, this kind of matrix. So the row is
picking the center going to be part of the problem, or are you going to pick the center separately? For example, by just considering each center and then computing the mean average distance to all the other.
No, we compute the.
I guess you don't know.
No.
So you couldn't do that. So you're going to have to discover what the center is.
Maybe I will ask this question in 2 or 3 slides.
Okay.
So I will explain about the distance to the next slide. Here I just want to explain how to express this problem in binary variable. That's all. And after I will speak about distance. So we want to fill this matrix. So this is the segment, and here this is the cluster. There is as many segments as cluster, because we can say that there is that each segment are a cluster. Okay. So if I want to say that this segment belongs to the cluster, I just to put 1 here. So this segment 4 belongs to the cluster 4, and the same for 9. This segment 9 belongs to the cluster 9. And if I want to say that this segment belongs to this cluster, I just to fill 1 here and 1 here for this segment. And after, I put 0 to the whole matrix. Okay? So we express in terms of binary variable the clustering. So now I will present the ELP clustering models, but I will begin by the end. I will present the constraint, and after I will present the objective function. So in this constraint, I just say that a segment can belong to only 1 cluster. I just say that if we take the sum of that, the sum must be equal to 1, because 1 segment can belong to 1 cluster. After, I just say that if a segment 5 belongs to the cluster 4, so the segment 4 must belong to the cluster 4. For example, I say that if I put a 1 here, so it's obligatory to put a 1 here. And the last and important constraint is to say that the distance between this segment and this segment must be below threshold. So it's very important because if the value is very high, so we can say there is only one cluster. If the value is very small, we can say that every segment are the same cluster. So we can try to search the best value. And after, the objective function try to minimize the number of clusters and try to minimize the dispersion intra-class.
W is the representation in some kind of feature space, and D is the distance.
Yeah. So W. Okay. So W is the I vector. I don't speak about that, but you can use what you want. I vector, speaker-embeddings, by example. You can use what you want. So it's most important is the distance between two segments, and X is the binary variable, the table.
So K is in cluster N, and K and N center, or points out to be cluster. Okay.
So this is the segment, and this is the cluster. Is your question?
Yeah, I'm just trying to understand that. Right. So the segment and the cluster. If that's a 1, the distance has to be small.
Yeah. It's like to fill a matrix. Huh?
Mm-hmm. Yeah.
So in your example, wouldn't it be xkn minus xnn is less than 0? Because you gave the example of row 6, column 4. So k is 6, 4 is the column n. And then you said that induces that row 4, column 4.
Yeah.
So that would be
This
4,
constant?
4. Right.
Yeah, I just say
k x n n, not x.
no. Sorry for your question. It's the opposite. Huh? So this is the cluster and this is the segment. Huh?
Oh,
So I say if the segment is in the cluster,
But they're not matrix indices.
yeah.
matrix.
Yeah, it's the opposite, but it's
They're just variables.
So, and after we just to minimize the number of clusters and the dispersion class of each cluster. Yeah.
What properties do you have to assume for your distance measure? Does it have to be a true distance measure, obey the triangle inequality, that kind of thing, or the D?
The distance measure,
Yeah.
but in fact it's a PLDA with I vector.
Well, I'm asking, can you substitute other distance measures in there? Do they?
Yeah.
Is there part of the derivation that it has to be a distance measure, or can it be a pseudo distance measure?
I don't understand your question. It's my English.
Okay. So you can have functions that behave somewhat like a distance measure, but don't obey the triangle inequality property.
Yeah. No. The PLDA. I think the PLDA don't. You say if you so there is 3 segments A, B, C, and if you calculate the distance between A, B, and B, C. It's inferior to AC. Is that your question or not?
Is that required?
Okay, no, it's not required that, because I think that the PLDA not follows this inequality.
So
But I'm not sure about that.
What is required for this derivation to work, for this system to work for D?
No,
What are the restrictions on
you
D?
can use what distance measure you want. So I use so PLDA, but also I use other distance metrics like cosine, Mahalanobis, and different other metrics.
Probably as long as it's non-negative, you put it whatever heuristic you want. Right. You put whatever heuristic you want, as long as it's not non-negative.
You can use what distance measure you want.
The third constraint kind of redundant to the minimization criterion.
Sorry.
So the third constraint,
Yeah.
that's going to determine sort of how many clusters you have, because if you set D.
So if you say that the threshold is very high,
If you set D small,
it's small, so there is
then
the number
then
of
you can have
segments
a
is
lot
equal
of
to the number of
clusters.
clusters.
No, wait, so now I'm confused. The third one might not be satisfiable, right?
So I can say that a point, so the distance of two segments.
All right, so if I
Can-
make
can-
D, so it's hard when D is small.
Yeah,
Yeah, and as I make D smaller,
yeah, because
then this may force more clusters. But isn't that redundant to what's going on in the minimization there?
so
Where if you put a very high weight on that second term in the minimization, it would effectively do the same thing as the third constraint. Like, why do you need that hard constraint?
you can I agree. You can remove this constraint and remove during the creation of the problem. You can remove all the
That one,
this point.
yeah.
You can do that, and in fact, when we use the speaker diarization in closed show, so in closed show, by closed show, I just want to say that we do a speaker diarization, not a single show, but multiple show, and we try to detect the recurrent speaker. Okay, and when we do that, we remove this constraint and we modify the program in order to speed up the process.
But the more constraint you put in, the faster your algorithm will run.
Yeah.
So is this constraint only aiming at speeding up, or is it also aimed at improving accuracy?
Yeah, the accuracy is the same.
Oh, so the third constraint is only
accuracy-
to make things faster?
Yeah, we can just remove that, but the accuracy is the same.
Okay, so that's very important. So this is just a speed up, just proving it.
Yeah.
Okay.
So okay for that?
So sorry, I don't understand why the accuracy will be the same. I think the final number of clusters will be determined by the delta you choose, right?
Will be constrained by the delta.
So the number of cluster is constrained by this threshold.
Right. So if you choose different threshold, then the number of clusters you get will be different, right?
If I change the value,
If you change the value of
the number of constraints is different.
you will get different number.
Yeah,
of
yeah.
clusters.
And then, therefore, if you remove that constraint entirely, the number of clusters will be different.
Yeah.
And therefore, the accuracy will be
It
different.
will be different.
You're saying the constraint is not really needed to get best possible accuracy, it's just needed to make things faster?
No, this constraint is only to if we remove this constraint, it's only to speed up the process.
Only
But we need to remove all the variable in the ELP models. Okay.
Oh, I see.
Yes, we cannot remove this constraint without remove all the variable.
Okay, how about we move on?
By example, I just want to so if xn is superior about this threshold, we remove all this variable in this problem,
Right, yeah.
and we obtain exactly the same accuracy.
Mhm.
But we remove one constraint, so the resolution is more fast. It's faster.
Okay.
Oh, but you change the sums. The sums are no longer over everything.
Yeah, we can change the objective function and change
Oh, okay.
this constraint also.
That cluster drops out.
Okay, so lots of variations here.
Also, this is my experiment. So we use around 300 hours of world-class news. It's French world-class news. So the evaluation dataset is Roper 2013. It's classical. We use an UBM of 120 for Gaussian. The I vector if dimension 200, and we use net normalization plus PLDS scoring. So the matrix is diarization error rates, is in fact a combination of 3 errors, miss, false alarm, and speech error. And I use the Lune speaker diarization toolkit. For the LP, I use the GLPK toolkit. So first, we compare the bottom-up algorithm with cross-likelihood ratio. So, sorry, I just want to mention that this is the name of the show in the corpus, and this is the overall diarization error rate. So we compare bottom-up with cross-likelihood ratio with I vector. So we obtain a gain, and after we compare bottom-up algorithm with ILP clustering, and we obtain a new gain with the ELP.
I have a quick question about using the I vector to measure the distance between two clusters, right? So is that because that your test the corpus say or has a longer segment, so you can get a reliable I vector score? Because if there's some conversation, then each segment is too short.
Okay. So in broadcast news, the segments, the mean duration of the segment are around between 1 and 2 seconds.
Well, short.
Yeah, it's
So
very
you're
short.
basing your I vector on
But-
1 to 2 seconds worth of speech.
Yeah, it's very short, but we obtain close results.
The I vector is computed, there's a separate I vector for each segment.
Yeah.
So actually, I don't quite understand what's the meaning of HAC here.
HAC, it's
Hierarchical.
hierarchical
Hierarchical
algorithm.
clustering.
Agglomerative.
Yeah, it's bottom up.
Okay, but there are other popular clustering algorithms there, right?
Yeah, it's a classical approach in for broadcast news. It's the baseline.
No, I mean, there are many other clustering algorithms.
Yeah. For broadcast news, we the classical approach is to use bottom-up algorithm and CLR for broadcast news.
So what's
Is-
the tuning criterion? The evaluation criterion here. Is this 12.03 the error rate?
Diarization error rates.
Diarization error rate, okay.
I forget this. Diarization, I should probably know this. Does diarization error rate include the speech, non-speech accuracy?
Yeah, it includes the speech non-speech, but in fact, in this kind of diarization, we just in fact, the segmentation is the same because we just change the speaker clustering. We just change the method of speaker clustering. So yes, the diarization error rate combines the three metrics, but in fact, we just compare the one metrics.
Segmentation.
Yeah, the clustering. We compare in fact the speaker error clustering.
Right.
But here I just indicate the diarization error rates.
Okay.
So another question is, to achieve this 12.03 value, do you need to adjust the delta in the constraint?
Sorry.
You have a constraint with the delta, right? It's a threshold. You have a threshold, distance threshold.
Yeah, sorry, I don't understand.
The third constraint that we talked about.
Yeah.
You need to adjust the delta for this result.
Yeah. So I don't mention, but we have a development corpus, and we optimize all the results on the development corpus. All the thresholds are optimized on the development corpus, and we apply we take this threshold and we apply that on the test corpus. Is it your question?
Yes.
Yeah. So I forget to. I have a curve, and I forget to present the curve. But yes, I have a curve, and we indicate the diarization error rate in function of the threshold.
Okay. So my question is, if you adjust the number of clusters in the other approaches, are you able to get better results?
So for this for the ELP, in fact, if I try to search the optimal threshold, it's exactly the same as the development corpus.
No, I'm not talking
No,
about
it's not a
ILP,
question.
I'm talking about HAC I vector.
Yeah, I don't know for that.
You didn't tune the
Yeah,
cluster.
I didn't try to research the best solution in the test corpus.
But in
I
the
just
you did it on the development side.
yeah, it's optimized on the development on the
In all three
development side.
columns, you
Yeah, yeah.
optimize on the development side.
Yeah, but your question was to optimize the threshold on the test set.
No.
No. Okay.
Because you have this free parameter, the choice of the parameter will affect your final result. And so in the other approaches, you can also adjust, for example, the maximum distance between two clusters and things like that. You can also control the number of clusters you can generate. So that will also affect the result in your baselines.
Yeah.
So I'm wondering whether you do the similar thing for baselines.
No, it's clear that I optimize all my results on the development corpus.
Okay.
So
So it's a fair comparison.
so
And and on the same development corpus.
you need an initial segmentation, right? So
Yeah.
you need to generate the segments that you submit to the clustering. How did you generate those, and were they the same for all your different methods?
Because the segmentation was done by the new speaker diarization. So
So is it some kind of so it's just a speaker change detector, right?
yeah.
So you basically look for speaker changes, and then any whatever comes between two changes is one of the segments that you'll feed to your
Yeah, I give that in speaker clustering.
And it was the same for all of the methods.
Yeah.
Okay, so you didn't do this method like in the ICSI diarization system where you generate clusters and then you use those clusters to resegment the data iteratively. Right, so you have some segmentation at some stage in your algorithm.
Yeah.
You generate an HMM with cluster models, and you use the Viterbi to segment to resegment the data. Then you redo the clustering and so forth. So you iteratively resegment and recluster. You didn't do anything like that.
No.
You just you found the speaker boundaries once, and then you simply do the clustering based on that.
Yeah, I know that in meetings you do that.
Right.
But
So for broadcast, that's enough? I mean, that's sufficient? You don't have to
yeah,
do the
we don't
segmentation?
need to do that in broadcast news.
I see. Okay.
But it's clear that in meetings you do
right.
that.
Okay.
So yeah, to finish, the thresholds are optimized on the development corpus. So I will speak about speaker embeddings. So one of the limits, does anybody?
Where has that gone? Are you using it now? Was it adopted at Marseille or at Avignon?
So the ILP clustering was developed in Lyon.
Who's using it now?
The ILP clustering. So there is some guys in IBM. So the Lyon use that. Orange, it's and I know that Najim use that, and Patrick also use that.
We should try it.
Is it possible I can ask you two more questions? We go back to the last slide.
Yeah.
So the first question is based on your initial speaker change detection.
Yeah.
What is the best direction error you can get?
So if
based on your initial speaker change.
Yeah.
What is the best direction you get?
What is the best achievable?
Okay.
Diarization error. If you had like an oracle to tell you the best clustering.
Each steps have an error. I don't know. I do the test one time, but I never redo the test on this corpus.
Okay, that's fine.
So
That's a good question.
I know that if we obtain the best clustering with this segmentation on this corpus, I think it's around 10% of diarization error rate. But it's 10% because there is some problem of speech overlapping in this kind of corpus that the system does not take into account. So there is some problem. So is it your question?
Okay, yes. The second question is actually, so how fast runtime compare column 2 and column 3?
ILP is very fast. It's more fast than hierarchical algorithm, like bottom-up. By example, for bottom-up and I vector, you must merge, and you must recalculate the I vector, and etc. So with ILP, you just calculate one time all the I vector, and you do the clustering.
What package do you use to solve the linear program?
GLP. It's a toolkit on Linux, a free toolkit, and it's very fast. And we do some tests in crowd show, around 150 hours of shows, and it takes around 10 minutes. I'm not sure about the time, but it's around 10 minutes to solve this kind of problem. It's very fast, because just because we remove in Crush, we remove this constraint, we remove this binary variable, and after we do not solve this problem like that. We try to separate the problem in n sub-problems. I don't explain that, but I can explain later if you want.
So what's the scaling with the number of clusters? So if you double the number of clusters of initial segments, sorry, if you double the number of segments, how does the runtime of the clustering?
I don't know, because it's very, very fast.
Right, but I mean, theoretically speaking, is it quadratic or linear?
No, it's linear. It's not quadratic. It's linear.
Okay. Because the number of variables is quadratic, right?
Yes, but as you use the PLDA matrix, you can remove lots of binary variable. Yeah, I'm okay to say that this matrix, if you increase the number of speakers, number of segments is quadratic, but as you use a discriminant distance, you can remove a lot of binary variable, and just to focus on the important binary variable. So I say it's not quadratic, it's more than linear. So I just want to speak about speaker clustering. So one of the problems about high vector, so high vector PLDA obtained very good results in NIST evaluation campaign, but we know that when.
Which evaluation was that? On broadcast news again?
No, it's on. I speak in January in speaker verification. And it's just an overview. Just okay.
Yeah.
But we observe that on short segments, the performance degrades rapidly. So there is a lot of work that try to tackle this kind of problem, to take into account in PLDS scoring, to normalize the I vector about the rate of the segment. And me, I propose to, because the I vector is extract on the total variability space, and me, I want to extract the features on the speaker space, so directly in the speaker space. So in order to do that, I propose to learn to extract this feature representation with a deep neural network. So I take a deep neural network. So the task of the deep neural network is the speaker identification task. So in the input, this is the first order Ball-Welch statistic. So we take a segment, we take a new BM, we calculate the Ball-Welch statistic, and after we normalize by the mean and the covariance about the UBM. So we give that in the input of the deep neural network. So the output is the speaker identification. By example, if the segment is the speaker ID 3, we say 001, 0000, etc., etc. And after, I propose, in fact, to use one of the hidden layer like a new representation. So, by example, if I say this hidden layer is a representation, so I compact the number of neurons, and I take this hidden layers like a new representation. And I call that the speaker embeddings. So, just to, in order to, so this is the speaker embeddings. So for the presentation, normally speaker embeddings are a vector, but for the presentation, so I must to compact the vector. And we see that there is some patterns that are in common with the different, so this is a train and test corpus, and we see that there is some pattern similar between the train and test corpus, just for information. So one of my goals is to replace high vector by speaker embedding in the high vector PLDA pipeline. So one of the problems is that the speaker embeddings is built without any Gaussian pre-absorption. And there is a problem because the PLDA assumes that all the data must be Gaussian. So we observe that every color represents the speakers. So I take 4 speakers, and every segment, every point represents a segment. And we observe that there is a radial distribution of the data. So it's clear that the cosine scoring, focus only on the direction proximity. So the cosine must be adapted to this kind of task. But I try a techniques. This techniques was used in speaker verification. It's a light whitening normalization, and in fact, this technique consists to artificial Gaussianize the data in order to remove the mean and to multiply by the whitening of the matrix. So, for the experiments, so I use the same background training dataset like the previous experiments, but I use another dataset, is ETAPE 2012. I use the same UBM. The vector of dimension 1, no, it's a mistake, it's 200, but the speaker embeddings of dimension 500. The I vector, I light whitening with 2 iterations, the speaker embeddings with 1 iteration. For the speaker diarization, we use the same toolkit. For the DNN, we use the CalD toolkit. The activation functions are ReLU, and we use 3 hidden layers. So first, I just want to compare. So it's exactly the same. Here I indicate the different show, and this is the overall of the test dataset. So in the first experiment, I just compare I vector PLDA with speaker embeddings cosine, and we observe that there is a gain. And after, I just try to normalize the speaker embedding with the light whitening normalization, and I use this speaker embeddings normalized with PLDA. So it's the same results. If I use speaker embeddings with no normalization and PLDA, we obtain worse results. If we use speaker embeddings with 1 lightning iteration, we obtain a new gain. And with 2 or 3 iterations, it doesn't work. That's all.
Why is no norm result is different from the previous slide?
No, because the last slide I use the cosine. And in this slide, I use PLDA metrics. So it's clear that PLDA doesn't work because there is no Gaussian assumption.
Could you apply the same thing to the I vectors?
Yeah. I vector is length white normalization.
Already?
Yeah. I don't. They are normalized. So for the conclusion and perspective, so for the ELP clustering, so one of the conclusions is that ELP clustering explore more clustering solutions that greedy bottom-up algorithm. So when I was in postdoc in Newman, so the systems that I developed with ILP has participated to the ETAPE 2012 and Repair 2012 and 2013 evaluation campaign, and we obtained the best results in single and cross show. And one of my perspectives with the ELP clustering is to make a joint model with speaker clustering and speaker identification. By joint model, I say when, by example, if you do a clustering, and so you make an identification in order to know the name of the guy, so you can do that jointly at the same time. And maybe we can do that with the ELP clustering. So for the speaker embeddings, so fixture extract on speaker space, and I don't present the works, but we will try to test with automatic speech recognition. By example, when we try the acoustic models, we try the acoustic models, and we also add the I vector. And so we remove the I vector and we use the speaker embeddings, and it works better than the I vector. And we try to use speaker embeddings in the speaker identification task, and it works more than I vector, and it works also very well with speaker diarization task. One of my perspectives investigates the use of different input filters. So we can, by example, use the input of DNN I vector. By DNN I vector, I just say that use the posterior probabilities of the given by the DNN and use this input vector in the DNN. And another perspective is to create a DNN to automatically learn the input vector. And one of the approach is to use this convolutional neural network text classification. Thank you.
So we have time for a couple questions.
So in the ILP case, so you have this. There's a few hyperparameters that sort of I assume will kind of empirically set how many clusters. Will favor some number of clusters. I guess the question is there a way in the framework to incorporate prior knowledge this way? So for example, without having to retune all the hyperparameters on a dev set. So for example, let's say you have some collection of data where you know that the typical number of speakers is the clusters you should have is between 5 and 15, and there's another data set where it's between 1 and 5. But you don't want to each time you don't have to go retune all the. You don't want to have for each time you have a case like that, you don't have to have a dev set and hyper tune all the parameters offline. Yeah. So is there a if you have a generative model approach like clustering, there may be a way to put a prior kind of in. Is there something like that in ILP?
I'm not sure to understand your question. So you have some data set with 1 to 5 speakers, and another data set to 10 to 15 speakers, and you want to adapt your systems.
So it's possible that to get the best performance on one set, you'd have one set of hyperparameters for your
and
a different set of hyperparameters. But you don't have to do that every time. Is there a way to?
If you know approximately the number of clusters, you can add that in the constraint of the problem. You can say, okay, for this kind of problem, there is between 1 to 5 clusters. And so you can add this kind of constraint in the ELP. But for me, the threshold that you learn, for me, this threshold is, in fact, represents the distance of an average of a speaker. So it's for me it's optimal to what kind of corpus you want.
So that one's independent of, should be independent of clusters. Those are overall cluster size.
Yeah, it's a mean of the speaker, in fact.
So do you observe that in your tests? So you have 10 different shows, right? Did you try to optimize that for every show individually?
Yeah. In fact, in all this show, this kind of show is very different because it's a show of pop star, and it's explained why we obtained very bad results. And in fact, I try to optimize my threshold on all the corpus without this and the opposite. But in fact, the threshold is practically the same.
Okay.
So I take all the corpus and apply the same thresholds on all the corpus.
So if it's not a threshold, so why is that one so much worse? Is it the I vectors are not?
No. It's very because it's the segmentation. Because there is a lot of music, so the format is 5 minutes, a lot of music, and it's very it's not usually like.
So is it that there's a lot of back and forth between
Yeah.
So short turns as opposed to. I mean, this goes back to the question: would this work on like meetings?
Yeah.
Maybe you have a lot shorter turns, and you don't have as segments that are long enough to estimate stable I vectors.
Culture and you.
No, I removed the test in my computer, so I can show you but yes, there is very short and a lot of music. So in fact, the error are given by the segmentation. The segmentation is very bad because in the segmentation it says that there is a segment but with a lot of speakers. And sometimes there is a segment, and also we have some problem with the speech and non-speech. They say, okay, there is non-speech, but the speaker speak and.
So on a different topic, this is a very general way of doing clustering, the ILP, the insight that you had.
And I hope that is a classical approach.
What else have people been clustering with ILP?
What else?
So is this the first application of ILP to clustering?
Yeah, I
or
see.
has it been used like to cluster documents previously, or used to?
No, I don't think that we are using documents. So yeah, I tried this kind of approach, and it's never been used in other fields.
It's never been used in other fields. So
It's only in speaker-embeddings.
Okay, so that's a real innovation. And have you seen it since applied to other areas, or do you think it would be applicable to other areas? I mean, it seems like anything that we currently say use k-means clustering, we could use this.
No, but
So-
I thought k-means might do much better than this one in many cases.
So when I explain Europa, and when I do the propagation of the identity, I use ILP in order to propagate all the identity, and it's based on my ELP clustering. So we can do, and we can apply another task like I don't know. Yeah, document clustering is possible. Yeah.
Okay.
But k-means has a limitation.
But isn't
It requires distance, true distance metrics.
Well, but this HAC is essentially k-means
No, it's not.
plus
It's
emerging stuff.
No, it's a hierarchical, so it's a greedy search stuff. It's different from k-means.
Well, because you don't know the number of clusters.
No,
You just merge, you don't iterate.
right, you don't need to, you only merge,
No.
that's it.
With the ELP clustering, you don't merge.
So it's very
Well,
different.
you have the
Because
stop
HAC.
problem, right? So in hierarchical clustering, you have to have a separate criterion for knowing when to stop clustering. What is the corresponding
What is the
parameter in your system? Right? So the general problem in hierarchical clustering is knowing when to stop clustering.
yeah?
Right? When do you know you have the right number of clusters, which of course is somehow related to the number of true speakers in the case of diarization. So in your system with ILP, what is the corresponding parameter? How do you control how aggressively you want to cluster things together?
By this threshold.
Is it the delta?
Yeah.
Is it the delta? Okay.
Isn't it
I control that as
the F also?
The goal.
Well, yeah, you're right. There's the
There's
weight
the F
parameter,
also.
the F parameter. The
Yeah,
weight.
I control
That's
that.
the ambiguity I was talking about before.
Okay.
They both seem,
So-
I think you could get rid of the third thing and just use F.
I say.
Well, that's an
if you,
efficiency. The delta is to rule out, to eliminate variables. Yeah, exactly.
Yeah,
So it's an
you
efficiency,
eliminate. You just you have this delta, okay,
Right.
but you eliminate. You can eliminate this constraint,
Mhm.
but you eliminate all the binary variable, and you eliminate by this delta. So you must to have an hyperparameter, and you control the cluster with that.
And you had a separate data set to tune those.
Yeah. The development set to tune this hyperparameter, and after I apply that on the test set.
Have you tried to re-optimize it? So how far from the optimal value were you after you tune those parameters? Have you found out?
So for the true corpus, Robert and ETAPE, in fact the hyperparameter on the test and dev corpus are exactly the same.
Really? Oh, okay.
But maybe in another corpus the development
Well, it'd be
hyperparameters
interesting
are
to
different.
take English broadcast news or something and see if the same parameters would work.
Yeah.
Yeah.
So this criterion is the minimize, right? What you minimize is a very generic criterion. I think it's very similar to all the other clustering approaches, right? That's just number of clusters plus some distance thingy. So your method is not about the criterion, but it's about finding the correct solution, or it's an optimization problem you're solving, or is it the criterion that gives you the good result?
Good question. For me, it's to optimize this. I want to optimize this, that, and this criterion is just to say that to constraint to say that a segment to like to create a model, a speaker model, to say that okay, all
Yeah, I
the
understand.
speaker model is the same.
So my question is, the same criterion, the first formula, you could also optimize that with k-means, for example, right? I think.
Yeah, we can do that, but there is a problem of initialization of the camins, and this is a problem. And I test that on camins, and I run several times the camins, and I obtain different results. But with the LP, we obtain each time the same results.
You actually did that experiment. You actually
I do that. And after, I try to different objective function. I try to minimize the interclass dispersion and to maximize the interclass dispersion. And I try another objective functions that try to maximize the number of speakers and to minimize the dispersion intraclass. But the best results are obtained with this kind of approach.
So you can also, I think, apply the same criterion for HAC, right? For the hierarchical clustering.
Yeah, we can, but the problem is with bottom-up algorithm is if we take the bad decision one time,
right.
So this is propagate.
Right. So what you're saying, your solution really is a search algorithm. That's what you're solving. You have the best way of solving the same equation, basically, the same criteria.
You go first.
So can you say a little bit more about this? When you do about how anything in particular about the cross-show?
Yeah.
Diarization, is that done just treating two shows as one big broadcast, or one then the other, or yeah?
Yeah. So it's an additional slide. So in single show, you treat the problem like that, like I explained my previous slide. And in cross show, you take, this is the show A, the show B, and in fact, you want to detect the recurrent speaker. By example, if you treat show A and B separately, you can say that you cannot detect that this speaker and this speaker are the same, but you, by example, can detect that this speaker and this speaker are the same level, but are not the same speaker.
So identity just means label.
It's clear or not what I say?
So when you say same identity, you mean same label? But
Same,
not the
the
same
identity
person?
is the same label. Okay.
So they're both speaker one, but
Yeah,
not the
yeah.
same.
So you say that, but so in cross-show you add a new steps, 4 steps. It's a clustering, but a global clustering on all the show. So you treat the show separately, and after you add 4 steps, global clustering that treats all the data. And now you can detect the recurrent speaker and say that this speaker and this speaker are not the same. We try to do that.
But you're not re-examining the identity decisions you made within the show.
Sorry.
So when you do the cross-show clustering
Yeah.
with ILP, do you reconsider identities within the same show?
So we try the experiments. We try to fix the clustering, and we try to reorganize. So, and in fact, to not to fix but to reorganize works better, because I think that in the first clustering we miss some.
So by the way, do you have explanation why you have this radio distribution? I don't understand that. The
Sorry.
radio distribution.
So radial distribution.
Radial distribution. The radial distribution of the I vector.
No, I don't
You
have.
don't know why. You have an intuition for it?
Could you show the picture? Yeah.
So this is a radial distribution of speaker embeddings.
So I've seen that before. Jeff Hinton gave a talk here
No, this is not
some
T-SNE.
some years ago and said he was like showing word embeddings or document embeddings, and he made a big deal about, oh, look at this, it's radial.
Okay, so why is it radio?
Wait, this is
I don't know.
distribution. class.
I don't know why it's radial distribution, but we observe that. So, in fact, the first experiment was to know if the speaker embeddings was Gaussian or not. And at the end, we observed that this is radial distribution. But we don't know why.
But this is a.
This is a radial distribution of speaker embeddings.
But this is how did you, this just is this like the first 2 dimensions or is this a projection?
Yeah. So it's we take 4 speaker, randomly 4 speaker, all the segment, and we use a PCA to project in 2 dimensions.
Doesn't this suggest to incorporate some kind of length normalization directly in the objective function of the training?
In the objective function of the deep neural network?
Yeah.
Yeah, maybe.
Also, the length has to do with the length of the segments. I mean, how far you are from the center, that is related to the length of the segment.
I don't know. But maybe we can add some normalization between the hidden layer.
No, because the input is length invariant, right? So the input to your network are the Baumgarten statistics. Essentially, it's the old I-vector statistics, right?
So it's exactly the same.
Yeah. Okay.
So my question basically is why they converge to the same point. You have a point.
But that's a
all
good
4
question.
speakers.
There's got to be some physical correlate to the distance from this origin point.
Is that 0?
I don't know. No, it's not 0. I don't know. Yeah, maybe I must to indicate the value of the legend.
Okay, let's thank the speaker again.